So I'm going to be talking about statistics and machine learning. So today we're going to start more with the fundamentals of probability. Then tomorrow more about making confidence intervals, and then the day after on machine learning. I put on here one of the, a recent result from NOVA. This is from a recent sterile analysis. And, we do a lot of work, right, in our analyses. And in the end, the summary of everything we do is just one of these, right? So ultimately, constructing intervals to say what things are allowed is basically the task that we're trying to figure out in the end. So I just wanted to give a little bit of a motivation to why we do all of this, because one of the things that comes up a lot is, why can't you just get an answer, right? Like, why do you have to do all of this work to get something? And the answer is that what we're interested at a very high level, right, is what role neutrinos play in our universe, right? We want to know how neutrinos impact, just the structure of field theory, right? Things like that. But to do that, we need to measure high-level parameters, right? So we need to measure things like oscillation parameters and other things like that. But those things aren't directly in our data either, right? Even those things which are, we have the ultra-high level, which is like what theorists want to know ultimately. And then there's the things we can actually measure, right? Like things like oscillation parameters. But none of that is directly in the data. All of these are extremely derived quantities. So we have to think a lot about how can we know, really anything, right, in order to be able to make decisions and have confidence in what we're saying. So the first thing we have to do is be able to make sense of experimental data. And so I wanted to sort of walk you through a little bit what this looks like, right? Because there's, before you even get to the point of doing a statistical analysis, everything before that is also statistics, right? It's basically statistics the entire way through. So just so you know, this is one of the first NOVA events. So let me use a better color. That right there is a neutrino. NOVA is on the surface, so there's cosmic rays going through all the time. And so one of the things you have to do is you need to actually find those interactions in the big forest of all the cosmic rays, which is actually not as hard as it sounds. So when you collect data, what you get, strictly speaking, what you get is you get pulses of voltage, right, on channels, right? We know that those are coming from light detectors that are attached to the detector, and we know that those pulses are roughly proportional to the amount of energy that was deposited in each of these channels as a particle went through. So to some extent, what we know is that there are hits in time and space that represent an energy deposit in a particular location, right? So we collect things, we take in data, we get a series of pulses in time and space that represent energy. So the very first thing we need to do is identify what parts of this cloud are causally related to each other, right? And so this is the first step. I said we have all the cosmic rays with a neutrino. NOVA has reasonably good timing resolution. So we take all of our hits and we use just a very simple density-based clustering to cluster things in space and time. And cosmic rays happen at all times, but the neutrinos are coming from a beam that's pulsed, right? So neutrinos come during very narrow time windows. So just by cutting out all of that, the time that's not consistent with the beam being on, gets rid of most of your cosmic rays. So we do this first to sort of get groups of hits that we think came from something. Then we need to figure out where the neutrino actually interacted. Of course, neutrinos don't have charge, so you don't actually see that. So we use something called a Huff transform, where we take all of our hits and you basically you transform to a space of essentially slopes and intercepts, right? So you're basically taking all the points in your detector and trying to see what lines could go through all your points, right? And what tends to happen is that if there is an actual line of points in the detector, you get a concentration in a certain region for that. So we look for these Huff lines, and those things wind up giving us these sort of points of radiation, right? And the assumption is that if those are diverging from a point, right, that must be where the neutrino was. That's inferring a lot. That's not actually always true, right? That's only true if we have something charged that promptly came from the nucleus after the interaction. But if there was, then this can work reasonably well. And then we need to figure out what particles we have. So in the nomenclature of nova, we look for prongs, which is just the idea of an object which has a definitive starting point and moves in a direction, but you don't necessarily know where it ends. So we basically we cluster things radially around the vertex and find sort of energy that's coming out along well-defined angles. And we sort of merge those together to construct our particles. So in each of these times, these are using sort of some prior understandings that we have of what neutrino events and then particles do in your detector to try to isolate individual parts. Now, once you do that, you have to come up with some sort of event selection because you're not interested in every type of event that's in your detector, right? You're interested, one, probably in neutrinos, but you're probably interested in a specific flavor. If you're doing a cross-section measurement, you're probably interested in a specific topology, right? So we look for defining features in events. So, right, so for muon neutrinos, we look for the existence of the long tracks because muons tend to travel for quite a long distance before they stop. If there are electron neutrinos, we look for fuzzier, shorter showers because electrons do a lot of pair production and Bremsstrahlung as they travel, so they wind up being a fuzzier sort of object. And in neutral currents, we look for kind of the absence of those things, or possibly the presence of, basically the absence of an electron or a muon. But we use these to categorize what we're looking at. And then we have to figure out what energy things are. So I said that each hit is associated with an amount of deposited energy, right? But the amount of deposited energy depends on the type of particle it is, right? Only charged particles leave energy in scintillator or in liquid argon, and they do at different rates, right? So you could go from the amount of energy that you see in each detector element to the true energy of the particle, and then going back even further, the true energy of the neutrino that created this collection of particles we see requires several steps of inference, right? But we need to know the true energy because oscillations happen as a function of true energy, not as a function of anything you actually see in your detector, right? So you need to try to infer what the true energy is in order to do that. Now, once you do that, you're still not done, right? Then you need to do parameter extraction. As John was saying, that what you see in the near detector, right, is some combination of your flux and cross-section and efficiency, but we actually know almost none of those things well, right? This is the big problem in neutrino physics is our understanding of cross-sections is relatively poor because neutrinos don't interact very strongly, so we don't see a lot of them. They're hard to measure. The flux also, we're making this by, slamming protons into graphite and relying on strong interactions to produce things. These are things that we can't really calculate directly, right? So we try to measure things the best we can, but you've already heard from John what the complications are in doing those measurements, right? So we need to figure out some way to find something certain in this collection of uncertainties we have. So oftentimes we have both near and far detectors, right, where we are attempting to use our near detector to constrain uncertainties and use that to make inferences about the far detector so that despite the fact that we don't know these things, we can still make a relatively certain measurement at the far detector. And this is a complicated set of machinery. This description here that I have here is sort of our schematic in NOVA for what we call far over near extrapolation, right? So the idea is basically you take your near detector data, you try to put it into a true energy space, you separate it into different channels that you think these different channels oscillate differently, you construct a far over near ratio, you oscillate it, and then you undo your true energy to to reconstructed energy. And in the end, when you add up all your components, you get sort of a corrected prediction. So it takes the simulation, which may not be perfect, and tries to make it more consistent with what you actually saw in the linear detector. So, and then once you have that, you have to do a fit to find your oscillation parameters. Because again, the oscillation parameters are not in here anywhere, right? We look for deviations from, we try to find the set of if we apply oscillations, it gives us a change to our prediction, right? Which we try to find the best match between that and what we actually see in data. And from that, we can infer the parameters, right? So everything we're doing is extremely derived, is the point I'm trying to make. None of it is directly there in any particular interaction, sort of just for the taking. Okay, so every part of this is uncertain or stochastic. I say that, and or, because some of these things are uncertain because there's just things we don't know, but some of them are quantum mechanical, right? And it's not that we don't know, it's just they just happen differently every time, right? A neutrino, when it interacts differently every time. It's a probabilistic thing, right? So there are inherent probabilities embedded in doing all of this that just come from that. So in high energy physics, you always have that. And then there's the additional uncertainties, which come from the fact there are things that are just not specified fully, right? Things that we can't know fully. And to make any of our measurements here, we basically require probability and statistics, right? There's no way out of having to do this. And just to think a little bit about the difference between probability and statistics, probability is basically the study of how likely a given event is to occur. If you think about it, this is going from a model to predicting an outcome, right? So, so one way of thinking of this is forward. This is basically doing predictions or sort of forward modeling. And that sort of type of path is always easier, whereas statistics is more the inverse problem of probability, right? So statistics is saying, you have data, how do you go backwards to figure out what created that data, right? Like, how do you infer things that created it? So the forward-going way is always easier than the backward-going way, right? So essentially, if you understand probability, you can make simulations to make predictions, and that's it's not easy, but it's relatively straightforward, right? But then going from collection of hits you see and trying to figure out what things could have happened that would have led to seeing the thing you saw is very difficult and not 100% specified always. So let's start by looking at the fundamentals of probability. So colloquially, probability is how often you expect a given event to happen, right? So probability is something people have thought about long before they made it mathematically precise. So Kolmogorov basically came up with some axioms that, using set theory, to try to make rigorous the intuition that people basically had for probability already. So the idea is, and without being too specific about it, because it turns out this is actually, you can say these things and do a lot of math before you actually know what any of these things mean. And the knowing what these things mean is actually a place where there's real divergence in how probability is sort of understood. But the idea is, imagine you have a set S, which is our sample space. And within that set, you have a subset A. So the idea is that you can assign a real number to any given subset A, and that number is your probability. And that follows what we think probability would be as long as it satisfies these axioms. So the first is that real number is strictly non-negative, right? There's no such thing as negative probability. It doesn't really make any sense to say that. So the idea is for any subset in S, the probability is going to be non-negative. The other thing is, if you have two different subsets in S, and they don't overlap, then the probability of the union of those two subsets should just be the sum of the probability of the two things, of the two subsets separately. And then finally, the probability of the whole thing, the whole sample set is 1. Right, so this idea is saying that if you have, I mean, one way to think about this, if you have a collection of things that can happen, the probability of any possible thing happening is 1, right? And if you have things that are distinct types of events, then if one thing happens or the other thing happens, the probability of either of those happens is just the sum of the both, right? So these are sort of essentially taking ideas of formal logic and trying to turn them into sort of set theory in math. Now, like I was mentioning, the sample space S is deliberately left vague. And that's because it's somewhat ambiguous, and it really depends on your interpretation on what this will be. As I'm trying to explain some of these bits, I sort of fall back on an understanding that sort of gives away one of the interpretations, because it is actually very hard to talk about completely abstractly. But in general, S could be discrete or continuous, right? There could be a finite number of elements, there could be an infinite number of elements, the elements could be continuous, all of those things are possible. The elements can be vector valued as well, right? They don't have to be just scalars. And then a variable that takes a specific value for any element in S is a random variable, right? So you can think of these things as like measurements, right? So if you had a given event happens, right? That event has some probability of happening. That event can also be associated with an energy, right? So energy could be a random variable that is connected to each of these elements of this space. Right, and like I said, random variables can be multi-component vectors if every element is associated with several quantities, right? So if you think of these things as things that a neutrino can do in a detector, right? You have, they can have energies, they can have different angular distributions, they can have, you know, different particle multiplicities. It can be a lot of different properties that could be associated with every possibility that you have. Okay, so now if you have two different properties that each of your events can have, right? You can essentially talk about the probability of one, the probability of the other, or the probability of both. So one way to think about this is like, imagine if you have a pair of dice, right? And you roll them. You have whatever the value the first die says, and then whatever the value the second die says, right? So you have some probability that the first die is going to give you an odd number, right? And you don't care what the second die says. You have some probability that the second die has an even number, and you don't care what the first die says. But then you also have a probability where die 1 is odd and die 2 is even, right? So there's a probability of some sample, some subset of those events will be that kind of combination of things, right? And so this is the joint probability. This is the probability of the intersection of these two sets, right? So if you think about like, you know, A here is that first case where your first die is an odd number, but you don't care what B is, and then B is the subset of this sampling space that you care what B says, but not A. But then there's this part in the middle, which is where both conditions are true, right? Because that can generally happen. So that is, you know, the probability of A and B, but normally we just write it as P, A, comma, B, right? That's just the union of, or the intersection of these. Now, there's also, we can also have the case where if we only care about one of these properties, right? We're rolling two dice, but we only care what one of them says, then if you have your joint probabilities, right, then you can go from that to figure out the probability of just one of them, right? So if we have the probability of A being any value and B being any value, but we only care what B is, you can basically sum up every value, basically you say the first die yields 1, and then B is whatever value you want. Then the first die is 2, and everything says the other. If you add up every option for die 1, then you're left with just the probability of B, and then A is anything, did anything, right? So this is marginalizing, right? So this is the idea where if you have a joint probability, the probability of 2 distinct events happening, and then you sum up over one of them, you're left with just the probability of the other, right? Without reference to the first anymore. So this is basically taking a joint probability and making it not a joint probability anymore. If these were continuous, you would essentially just do an integral. You just integrate over the thing you don't care about, and you would get the probability that no longer references the event you don't care about. Okay. And now this is all getting towards the big question here, which is about conditional probabilities. So very often, the information we have is not actually a statement of joint probability. Oftentimes what we have is the probability of one thing happen given the fact that you know something else already happened, right? So you don't actually know the full probability distribution of both of these things at the same time. So the idea here is that if we know B is true, we're in this circle, right? So it's given B means that we're in that circle. We want to know what the probability of A is given B, which means that we want to take the area of that, but divide it by the area of just B being true, right? Because the full volume of A and B is not the thing we care about anymore, right? The joint probability is normalized by both of them, the volume of both of those sets. But the conditional probability is normalized by the size of B. So if we take the joint probability and we divide out by the marginal probability of B, that gives us the probability of A given the fact that B is true. Okay? And because this whole thing is reversible, the joint probability is symmetric, you could do the same thing the other way, which is saying that the probability of B, given that you know that A is true, is the joint probability divided by the marginal probability of A. Now, these both involve the joint probability of A and B, so we can solve for that and set that equal. And if you do that, you get sort of a fundamental theorem of probability, which is Bayes' theorem, right? This tells you how you can relate a conditional probability conditioned on one variable to a conditional probability conditioned on another variable. So this is always true, right? It's called Bayes' theorem, and you may have heard of Bayesian statistics. Bayesian statistics cares about Bayes' theorem a great deal, but this is really not, this is true always, right? This isn't strictly speaking only a Bayesian thing. This is, right, like I said, this is always true. This is a fundamental property. So just so you know, the language here, this thing we call the prior probability of A. This is the marginal likelihood, and this is the likelihood. I mean, if we interpret it a different way, say this. But this is something that like I said, is generally important. And to see why, the examples that come up are almost always medical, right? Because our intuition about how things work in medicine is actually extremely poor. Essentially, fundamentally, our gut understanding of conditional probabilities is not good, like in general. So this give an example, and there's a test, right, called the triple screen test. So when it is possible that, when a woman is pregnant, you can do a blood test to look for markers in her blood that are suggestive of whether or not the fetus has Down syndrome, right? That's oftentimes something people would like to know during pregnancy. Now, the triple screen test has a 70% sensitivity. That means that the probability of a positive result, given that that Down syndrome is present is 70%. It also has a 5% false positive rate. That means that's the probability of getting a positive test result, but Down syndrome isn't present, right? And then there's a 0.1% prevalence rate of Down syndrome in the general populace. So the importance here is that 70% sounds pretty good, right? But the question is, you don't actually care what the probability of getting a positive result is given the presence of Down syndrome is. That's not the thing anyone actually cares about. When a person gets a test result, they want to know is, if that was positive, what's the probability that the fetus actually has Down syndrome, right? That's the thing that people actually want to know, not the thing that these numbers tell you directly. So this is a case of trying to reverse the order of conditionality, right? We want to reverse which direction the conditioning happens. So let's think about this, what each bit is, right? So in this, in Bayes' theorem here, we can say the thing that we want to know is the probability that Down syndrome is present given that there was a positive test. What we know is the probability of a positive test given Down syndrome. We also know the prior, which is the probability that Down syndrome is present in anyone in the population, right? Because if we don't know anything else, right? If all we know, right, if we have no other information, our prior should be like, how often does this happen in people ever, right? That's like sort of should be your starting point. And then B is, what's the probability of getting a positive test for any reason? Now, the one last thing is that the probability of getting a positive test result is the joint probability, is the sum of two different joint probabilities. The probability that Down syndrome is present and there's a positive test result, and the probability that Down syndrome is not present and it's a positive test result, right? But of course, we don't have joint probabilities. We don't actually know what those are here. But we know how to get a joint probability from a conditional probability. So we can basically write this as the probability of a positive test result given Down syndrome times our prior that Down syndrome is present, plus the probability of a positive test result and Down syndrome is not present times the probability that Down syndrome is not present, right? And again, the probabilities add up to 1, so the probability that Down syndrome is not present is just 1 minus the probability that Down syndrome is present. So you put this all together, you just plug in all the numbers we have here, you get 1.4%, right? So if you get the triple screen, test done and you get a positive test result, there's basically a 1.4 chance that the fetus has Down syndrome. Now, that's a small number. It's basically an order of magnitude higher risk than just not knowing anything, right? Because there's a 0.1% chance of any given person having Down syndrome. Whereas now you know that the chances of this particular fetus having it is 1.4% chance, right? But it's still pretty low. Now, you can go further and think about, what if you had a second test that existed, right, that had a similar sensitivity and false positive rate? So maybe this is actually a good, well, I think I actually have it written down, so this won't be one of the questions for you to do. But the idea is, let's say you had a separate test that had a 70% sensitivity, 5% false positive rate, and everything else. How could you find out what the probability that the fetus has Down syndrome, given that that second test was also positive? So this is the case where, this is sort of where the real power of Bayes' theorem comes in, which is that before the first test, all you knew was that the fetus was a human being, right? And that human beings have a 0.1% chance of having Down syndrome. After the first test, you know, has a 0.4% chance, which means that your prior has changed, right? Because you know more now. than you did before. So if you use that new prior and plug everything into what you had before, you get this, which basically says that if you had 2 positive results, now it's a 16.6% chance, right? So again, this is still a relatively small, this is not certainty by any means, but as you've done this, your knowledge, your knowledge of what might be true is getting higher and higher, right? So this is, this sort of stuff came up a lot during COVID as well. I don't know. So one thing that, I don't know if you remember this part of it, but one of the questions that came up when you're doing tests is like how good the COVID tests are. And right, of course, the sensitivity of a COVID test doesn't change over time, really. But there is a difference between when there's a wave happening, right, and prevalence is extremely high. It really doesn't matter what the test says. If you feel sick, you probably have COVID. Because if you plug the prior in, if everyone else has COVID and you feel sick, you probably have COVID. It doesn't really matter. The test doesn't give you any other extra information. And if the prevalence is really low, the test doesn't actually add that much either, right? A negative on the test doesn't tell you all that much, right? So basically prevalence rates matter a lot because that's the prior that go into figuring out the thing you actually care about, which is the truth of what condition you may have. Okay, so now being sort of intentionally vague about what all these things in the set mean, and the reason why is because there are 2 main interpretations of what those things are. And those are the frequentist and the Bayesian interpretations, right? So the rules of probability and how you manipulate the math doesn't depend on your interpretation. But exactly what each of those bits mean is actually very different depending on the 2. And that does have consequences for how you do things later on. So the frequentist interpretation is that probability is the relative frequency of an event's occurrence, right? So you say, I have a given event, I see how many times that event happens, I see how many times all possible events happen, divide those 2 things, and that tells me the probability. Now that's just, that's approximation of the probability. We have to sort of take infinite statistics to get to the truth, but it's sort of a well-defined thing. Only the outcomes of measurements have probabilities, so we can talk about consistency of models with the observed data, not the probability of a model being true. It's just, that's not something you can actually talk about in the frequentist idea. Because the idea is a model is either true or not, right? There's no such thing as a model being sort of partially true. It's either true or not, and we're just trying to figure out if the things that we're seeing are consistent with a given model. The Bayesian interpretation is that probability is subjective. Sometimes people talk about it as like probability is basically like proportional to how much money you'd be willing to put down if someone were to ask you to bet on it, right? Because that's how much you believe it's true, right? So if someone said, how much, would you be willing to bet on something, and you're willing to bet a lot of money, you're pretty confident that you think that thing is true. And that's different for each person, right? That's not something that everyone can necessarily agree on. Different people have different feelings on how certain they are on a given event. So in this case, the sample set S consists of hypotheses. And it's constructed so that only one hypothesis can be true, but that the prior probability A is our degree of belief in any given hypothesis. And in this case, the Bayes theorem provides the machinery to update our degree of belief in a particular model, right? So the probability of a model being true given the data we've observed is proportional to the probability that the data of observing a given data given a theory times our prior probability in that theory, right? So the probability of the data given the likelihood, given the theory is called the likelihood of observing a particular set of data given a model is true, and the probability of the theory is our prior belief in the theory. So there are real consequences to sort of picking the interpretation. So in frequentist ways of thinking, probability is an objective thing. This is machinery for defining what you mean. And that is very appealing. But measurements of probability are only possible in the limit of infinite statistics, right? Which is not actually a thing that can be done. And we can't answer the question everyone wants to know. Everyone wants to know whether or not something is true. Frequentists can't say that, right? It's just not a question that can be answered. We can only answer whether or not we can reject a hypothesis, right, with a certain amount of confidence. In the Bayesian thing, the definition of probability is subjective, which is not something that we love in science, right? We would like there to be an answer that everyone can agree on. The answers can be highly dependent on the choice of prior. You can choose priors that no amount of data will ever overcome, right? So if you make a prior which is a really tightly peaked Gaussian, there's essentially no data that can ever change your mind. You run Bayes' theorem, you just get back the same thing over and over again, no matter what you see, right? So if you choose bad priors, you basically get bad answers. But it answers the question everyone actually wants to know, which is like how much should we believe a given theory? So it can actually answer that, but at the cost of requiring something that we don't love. So one of the good quotes from Louis Lyons is that frequentists answer a question nobody cares about, but with extreme precision, whereas Bayesians answer the question everyone wants to know, but with assumptions no one believes, right? So you sort of have to pick your poison between the two. But I will also say that, generally speaking, in the limit of infinite data, both interpretations, as long as you do everything reasonably, give the same answers. So if they don't give you the same answers, it usually means that you need to just do a better experiment, right? So when push comes to shove, that's usually the conclusion, is that they better give the same answer, because if not, you probably didn't do a good enough experiment. Okay, so let's talk a little bit about probability density functions. So these can be continuous or discrete. So a discrete distribution gives the probability of an experiment yielding a particular value, and it's a discrete number. Right? So this could be things like counts. A continuous distribution is the probability of x being your measurement being in an infinitesimal interval between x and x plus dx. So the probability is actually fx dx. And the idea here is that if you have a continuous distribution, the probability of any particular number is actually 0, right? Like any particular value, the probability of getting that value is 0, or at least infinitesimal. But if you integrate over a range, you can get a finite number. Now, those numbers, you'll see PDFs will still be a function that you can evaluate at different points, and that's because you can think of the PDF as being a relative frequency. So even though the probabilities are infinitesimal anywhere, the ratio of one probability to any other is actually a finite number, right? So you can still define this as a relative frequency quite nicely, even though the probability at any given point is 0. And then normalization, probabilities have to add up to 1. So in the case where it's discrete, you have to add up every option, and then it's 1. In continuous distributions, you have to integrate over the sample space, which might just be like the real numbers, for instance. So in general, anywhere you have a continuous distribution, you just replace a sum with an integral, and you're fine. Histograms, we use them a lot, but when they're normalized, are basically an empirical PDF, right? So the idea here is that this is telling you the probability in a given region, right? So this is approximating a PDF as a piecewise constant distribution. And then multi-dimensional histograms can be an approximation of a joint PDF, right? So this is sort of showing the joint PDF of X and Y in an empirical way. Moments, so the mean is a measure of the central point of a distribution, and so it's the integral over the whole sample space of X times the PDF. And the variance, which is a measure of the width, is the integral of X minus the mean squared times the PDF. The square root of the variance is a standard deviation, and that's usually what we take as a standard error. So for a Gaussian, the standard error is actually the parameter sigma of a Gaussian, and that corresponds to 68.3% of the probability. So we tend to pin the idea of a standard error to sort of what Gaussians do, right? So if we calculate the standard deviation, we use that as a standard error on a given measurement. Okay, so as an example, imagine you have a digital pulse. So actually, let's not say times. Let's imagine this is a detector element, right? We have some detector element that's a certain size big. It goes from one side A to another side B. And the question is, if we get a hit on the detector element, what is our resolution in space of that hit, right? So think that the resolution is basically your standard deviation, right? It's basically saying, what is our uncertainty on where that is? So I'll get you started, but I think this is probably something that you should do, do at home. So first of all, this is a uniform distribution. So that means that our PDF is a constant between A and B and 0 otherwise, right? We need this to be normalized. So it has to be equal to 1. If you do that integral, you'll get that C is equal to 1 over B minus A, right? Now, we need to know the mean before we can get the standard deviation. So the mean is equal to 1 over B minus A, the integral from A to B of x dx. Right, so this is going to be B squared minus A squared over B minus A, which is B plus A over 2. And so for uniform distribution, the mean position is just literally the average between the endpoints. Now, the thing that you should do is to compute this. And you should just make sure that you get that, but what you should get at the end is something like this. Okay, so you should verify that you get that, but the importance here is this is actually something that comes up a lot, which is when someone is trying to figure out an uncertainty put in, people will often use the full width of your element as the uncertainty. But in reality, you should be using the width of the element divided by root 12 if you think what you're doing is actually uniform instead of Gaussian. So this is sort of a common mistake people make all the time, is not remembering that this is true. Okay, if you have multivariate distributions, this generalizes pretty straightforwardly. You just write a vector sign over everything, and that's the answer. So your mean is going to be a vector if you have multiple properties that you're integrating over, and you need to do 2 integrals if it's a 2 component, 2 properties. And you can also use this to generalize from variance to covariance, which is actually a matrix. So the covariance between variable x and variable y is equal to this, or more compactly, you can write it like below. And this basically tells you the diagonals, so the covariance for x and x is just the variance of x. The covariance of y and y is just the variance of y. And then the off diagonals essentially tell you how correlated the 2 different parameters are. So you can write a correlation coefficient, rho xy is your covariance xy over the standard deviations of x and y, right? So the correlation coefficient is always between -1 and 1, where 1 is saying they're fully correlated, and -1 is saying they're fully anti-correlated, and then it can be anything in between. So this here is a case where you have 2 variables which are Gaussian distributed, but they're uncorrelated with each other, and you see something that comes out sort of a circular pattern. If you put in a correlation constant, this is a positive correlation because it goes tilted that direction. But this is basically Gaussian deviates that are correlated with each other. But just as a warning, the correlation coefficient quantifies linear relationships. It doesn't quantify all relationships. It's possible to have relationships between random variables which are very much real, but do not show up as a linear correlation. So the classic example is this one. So this is basically a set example where I did a uniform distribution in theta, but I did a Gaussian in R, right? So you get this circular distribution. This has a correlation coefficient of 0, right? The two parameters are completely uncorrelated with each other, but one is a function of the other. So just because the correlation coefficient is 0 doesn't mean that there is no relationship between your variables. It just means there's no linear relationship between your variables. There's no way in general to extract higher order relationships between different random variables. Okay, now just quickly some of the most important distributions. So the binomial distribution is the probability of finding little n successes in big N trials. So you have some process which has some probability of success, which we call epsilon here. And the question is, if I repeat this n times, how many times do I succeed? So you can think about this in saying that the probability of a given success is epsilon. The probability of a failure is 1 minus epsilon. So the probability of getting n successes and big N minus little n failures is p to the n, or epsilon to the n times 1 minus epsilon, big N minus n, right? Now you also have to have a combinatorial coefficient in the front, because we don't actually care what order these things happened, right? So if we only care that in the end there's a total of n successes, not the order in which it happened. So you need to take every different possible ordering and divide out by that, right, to get the actual probability. The mean number of successes is just the total number of trials times the probability of success, and the variance is the number of trials times the probability of success times the probability of failure. So strictly speaking, all bin counts are binomial distributed, right? We never say that, but strictly speaking, whenever you make a histogram, right, you have some event happens, right? You have some, like a neutrino interacts. The neutrino either interacts or it doesn't interact, right? It has a probability of interacting and has 1 minus that of not interacting, right? So strictly speaking, bin counts are binomial distributed. However, in high energy physics, it's almost always true that there's far more trials than there are successes, right? So we have the flux of neutrinos coming off the target is huge. The number of neutrinos we actually see is tiny, right? So in general, in the limit, there's sort of a continuum limit where you take the number of successes to infinity and the probability of success to 0, but in such a way that the product goes to a finite number, that in that limit, the binomial distribution becomes the Poisson distribution, right? So anytime we have a process which has a very low probability, right, but you have many, many, many trials, you can model this as Poisson. And that's going to be happening with, we're looking at like neutrino interactions at a detector or radioactive decay, right? There's way more uranium atoms in a chunk of uranium than the number of decays you actually see, right? So in general, anytime you have counts, we consider this to be a Poisson distribution. There are times when that's not true, but it's very unlikely to happen in neutrino physics. But like, for instance, if you were doing a collider physics and you had a saturated trigger where you were taking the probability of success was 1, and you were taking every single event, then that's not going to be a Poisson anymore, right? So there are cases where Poisson may not be a valid distribution, but it's but these are corner cases. It's a somewhat uncommon thing to have happen. So in this case, this is the probability of having n observed events given new predicted events, right? So nu is the probability of success times the trials, but we don't actually care about that. It's sort of, this is the average number of successes you expect in a given period of time. So you take data for a certain amount of time, you predict new events, and the number that you actually see is n, right? And this has the nice properties that the mean is just nu, the expectation value, and also the variance is also nu. And this is the sort of origin of like when we talk about like root n counting statistics. right, comes from the fact that the standard deviation of this is root the number of expected events. The Gaussian distribution is everyone's friend. It makes everything easier generally. And the Gaussian, it's nice that the Gaussian distribution is sort of the limiting distribution of Poisson distributions. So if the number of expected events is large, then the distribution is roughly Gaussian with a mean of the number of expected events and a standard deviation of root the number of expected events. So that's the origin of our root n error bars, right? So when you have a histogram and you put error bars on it, you always put error bars that are size root n, and that's just explicitly using this Gaussian approximation for Poisson process. This is continuous, not discrete like Poisson and binomial. So strictly speaking, the probabilities you need to integrate over like a full bin, right? So this gives us probabilities of fractional numbers of counts, and you want to integrate over a full count to find out the actual correspondence with the Poisson. So like I mentioned before, this has the nice property that there's 68.3% of the probability is located between mu minus sigma and mu plus sigma. Also, the sum of two Gaussians is also a Gaussian. So essentially, you have two Gaussians and add them together. The probability distribution of the resulting thing is a Gaussian whose means are just the sum of the two means, and the variance is the sum and quadrature of the standard deviations, which is basically how we add errors, right? And it originates from the properties of a Gaussian. Okay, just quickly the relationship between distributions. So this one is comparing binomial and Poisson. You know, if the number of successes is large, this actually agrees really well. This is showing the how similar Poisson and Gaussian are this is for n of 50. One thing you'll note is that often, as you will say, if you have more than 20 or 30 events, Gaussian approximation is fine. It's okay, right? Like, it's not as good as people say it is. So one thing to remember is that the Gaussian approximation is convenient, not necessarily like very rigorous. It takes a lot of events before it starts to be a really good match. Okay, but the other reason why Gaussians show up so much is the central limit theorem. So basically the idea is the sum of small uncorrelated random numbers asymptotically approach a Gaussian distribution. And that's true even for very non-Gaussian underlying distributions. So in this case, this is, I made a distribution which is two uniform distributions, right, sort of far apart. If I take 10 of these and take their average, you get this, right, which is increasingly non-separated. Then if I do 100 of them and take an average, it's basically indistinguishable from the Gaussian, right? So you can take pretty crazy probability distributions, and as long as you sample them a bunch of times and add them together, you wind up getting something that looks Gaussian. So this is the reason why Gaussian uncertainties are so common in statistical analyses, is that we assume there are many, many factors changing everything, and no matter what the form of those things are, when you add them all together, it basically winds up being Gaussian in the end anyway, which is, like I said, very convenient. The last distribution talked about is the multivariate Gaussian. So this is the n-dimensional generalization of a Gaussian. So I showed you sort of two correlated Gaussian distributions earlier, but this can go to n dimensions, right? So in that case, the covariance matrix basically replaces the variance as the thing sort of controlling the size of your distribution. So this I'm going to show later, essentially multivariate Gaussian likelihoods for doing fits, which is something that I'm particularly interested in. So this comes up a lot. The other nice thing is it's really easy to draw random numbers from a multivariate Gaussian. Essentially, if you can Cholesky decompose the covariance matrix, then you basically just take regular unit Gaussian random numbers, multiply it by the Cholesky decomposition, and add it to your mean, and it gives you things that are correlated Gaussian random numbers. there's just a little bit of a complication. This is strictly true if your covariance matrix is positive definite. Covariance matrices can be non-negative definite, right? They can have a zero, like you can have a covariance matrix with a zero determinant, right? And that's still okay, basically, but it gets a little bit trickier to handle. There's machinery you can use to handle cases like that as well, but it's essentially the case where you don't span the full space anymore, right? You're so full. If you're fully correlated, then really you only have one random number, not n random numbers. It's just one random number spread out over n of them. So there's a degeneracy there. So I don't know how long. Another 5 minutes? Okay, I can get through some more of this, and then we'll just pick up where I end. So now that we have probability under control, we can start talking about hypothesis testing. So it's important in the languages of statistics that we always, whenever we ask a question, we always need to phrase it in the context of a hypothesis, right? So oftentimes we want to know if something, we'll say something like, is there anything weird or anomalous going on? But that's a very nebulous thing. So instead we need to say, what is our default assumption? And that default assumption is our null hypothesis. That's the idea of, this is the thing we expect to be true. And the way we need to phrase things is saying, what is the probability? Basically, we want to know how consistent our data are with that null hypothesis, right? That's a question we can actually answer statistically. You can also have alternate models, so you can have many of them, but if we have just one, we call it H1 as the alternate model. And so often what we're doing is we're comparing the relative probabilities of the relative consistency of data with different hypotheses to make decisions. So one thing you can think of is, like, let's imagine you have particle separation. You're trying to separate particles in your detector. You have something that's a muon or a proton. That's not actually that hard to do, but you have some observable, right? So maybe something like the average energy loss per unit distance that you measure in your detector. And you want to know, based on that, which particle it is. So let's say that the muon hypothesis is our null hypothesis. We make a test statistic t, which is a function of our data, which is the thing that we're going to use to figure out consistency with our hypotheses. So what we want to know is, what is the distribution of our test statistic under our different hypotheses? So your test statistic can be lots of things. It can literally just be the observable, right? So in this case, if the observable is just the average dE dx, you can say, what is the distribution of the average dE dx of the particle if that particle were a muon, and what's the distribution of average dE dx if that particle were a proton, right? So you can do something like this, where you can say, this is sort of like, this is how that variable would be distributed if it were muon. This is how it would be distributed for a proton. So what you do then is you say, I want to define a critical region so that I reject the null hypothesis if my observed value of my test statistic is in that critical region, right? And we define that by saying I have some significance value alpha, which is the probability of rejecting the null hypothesis when it is in fact true, right? So we're making a mistake, right? So this is called a type 1 error, when the null hypothesis is true but I reject it. So if we know our distribution of our test statistic, then alpha is the integral of from the cut to infinity of this conditional probability. You can also figure out what is the probability of accepting the null hypothesis when actually the alternate hypothesis is true, and that's just the integral of the other distribution we have. So beta is the type 2 error rate, and it's the integral from negative infinity to your cut of the conditional distribution of your test statistic under the assumption that the alternate model is true. So you can basically, if it's a one-dimensional test statistic for a given significance, you can just compute from that what your beta is, what the rate of accepting H0 when actually H1 is true. And I think the last thing I'll just mention is that if your test statistic is not one-dimensional, right, if you have maybe multiple features that you're looking at, so in this case, let's say you have the average dEdx, but you also have sort of the average angle of multiple scattering and the length of the particle, right? Then there is some ambiguity about how you pick a region that has a significance level alpha, right? So there's actually many regions that you could pick that have significance level alpha, but would have different betas, right? So the Neiman-Pearson lemma basically says that the likelihood ratio produces an acceptance region that has the highest power. So basically, like if you pick your significance, right, which region of significance alpha has the lowest possible beta, okay? And that is always going to be pickable through this ratio of likelihoods, right? So the probability of your test statistic given H0 divided by the probability of your test statistic given H1, right? And if that is greater than some value C, then you reject it, or less than C, you reject. This is the acceptance region. The greater than C is the acceptance region. So you can often construct likelihoods this way, and this is going to be the core machinery that we're going to use for interval construction later on, right? When we sort of just do contours for determining sort of what regions are allowed for different fit parameters. Okay, so maybe I'll stop here and we'll pick up from there tomorrow.
Yeah, so you said that correlations are useful only when we have linear relationships between the two variables, let's say x1 and x2. So I was wondering if we look at the correlations between, let's say if x1 is a analytic function of x2, then if we plot x1, x2 square, like the powers of, then can we get some information about the function?
Probably, but what's normally done is when things are linear, right, you can basically come up with like a covariance matrix for your whole space. What's more normally done is that you can basically compute your covariance matrix over small regions. Because in a small region, all relationships are linear, right? Like as long as things are nice and smooth, if you go to a small enough region in space, things are nicely linear. So I'm not sure I understand what. Yeah. Mm-hmm. Right, so it's locally uncorrelated, right? So if you Taylor expand around a small region, and that coefficient is 0, that's basically saying that locally the variables are uncorrelated. But as you move around and do the Taylor expansion elsewhere, you can find. So if you do a circle, right? The global correlation is 0, but if you limited yourself to a patch, the correlation would change, right? If you're sort of walking along that circle, and you'd sort of walk around, and the correlation would change as you go around it. So you can define things like a local correlation. This is actually how like nonlinear fitters work, more or less. Is a nonlinear fitter makes a approximation, like a linear approximation in a region. It does linear minimization, moves to a new location, and then redoes it iteratively, right? So the idea of these things work as long as your functions aren't too badly behaved. These things work as long as you're in a small enough region. So all of these linear ideas, we wind up using. All of our nonlinear techniques are basically just iterative versions of the linear ones, where we just successively linearize the problem every time as we're doing it. I don't know if that answered the question. Okay.
Okay, last question.
Hello, sir. So in the hypothesis test, how do we interpret it alpha and beta in the case when two distributions are well separated?
if they're well separated, then basically, like if they're completely disjoint, then you can make alpha 0 with no problem, and you actually don't have to bring statistics into it at all, right? So that's a great situation to have, because then you never can mistake. Like if your probability distributions are actually well defined and you understand them well, and they do not overlap, then you can basically place a cut that gives you, 1 minus alpha is 100%, which means like, anything below your cut is 100% of the time actually null hypothesis, and there's no chance of anything actually being alternative hypothesis, right? So we place that cut and you say anything below here is 100% a muon, 0% a proton. We've done a perfect separation. So if in that case you would basically say you can basically make arbitrarily good significance, right? And
where
have
we
no
can,
fake rate at all.
where we can put the critical line from where we will say it is proton, it's muon.
What's that?
I mean, in which point I can put the critical value to say it is 100% muon?
So you can't do it here because they overlap, right? But if you had two probability distributions that did not overlap at all, right? Let's say these were compact distributions that don't have long tails, right? Then you could actually place a cut with anywhere in between, and beta would be 0 and alpha would be 0, and it doesn't, and that's a perfect separation. You don't make any mistakes. I mean, in reality, even if you have good separation, typically you'll have something like, you might have a very tight Gaussian core, but then a long tail, right? Where you have like, the tight Gaussian peak is like when you have a good reconstruction, and then you have this long tail of reconstruction failures, right? So like when I was talking about vertexing before, right? Where you do this thing where you bring in lines and sort of figure out your vertex. Like, I mean, oftentimes you have like a distribution where you have your vertex, you have a width of like a couple of centimeters, right? A Gaussian of a couple centimeter width. And then you have this long tail where it's like, you said the vertex was over here, but it was really like on the other side of the detector, which basically just means like you just made a complete mistake, right? I just did completely wrong thing. So in real life, there's always these long tails, because in real life, we took a bunch of hits and strung them together, and maybe we just put the wrong hits together, in which case the muon maybe it actually has some proton hits in it because there was a proton that went next to it, right? And so we misattributed the hits. So like I said, in real life, like this, I was just taking like a Landau distribution for like the average DEDX of a proton and a muon, but in real life with reconstruction, you might have a proton, but a cosmic ray went through, and the cosmic ray hit was right in line with the proton, and so the algorithm added it in, and so you have a DDX of a muon in the middle of a proton, right? So in real life, there's always tails, but if you were lucky enough to have distributions that were completely separated with no overlap, you could make a cut that had alpha and beta were 0 with no problem.
Okay. Thank you.
Okay, let us thank Adam again.